So, dear infrastructure engineers, today I'll be taking us through the water demand, supply, and distribution. I'll be looking at chapter 8. I know why I'm going to chapter 8, because I want us to do the real thing today. We've been able to do the introduction, we've been able to do the steps. Let me recap the steps once again. The step for you to design a water reticulation system for a district, for an estate, for a region, is by you getting a map, the map of the place and the topography of the place. You need the map, you need topography, you need the layouts, you need the history of the place, you need the studies that have been done so that you can use it to write your report and everything. And when you've gotten the map, the topography, the next thing is you do the water source. Where is the water coming from and where is my elevated tank going to be? We said that 90%, 95% of water distribution systems are done by gravity. So in your layout will help you to establish the highest point and the lowest point. Expectedly, the lowest point is going to be the point of water source because water flows at the lowest level. Then the highest point is going to be the location of your overhead tank. So you will establish two things. And since it's going to be by gravity, it means the difference between the lowest point and the highest point gives you the pressure of your network. So if the pressure of your network is not up to 2 or 3 bars, depending on other conditions, then you now know how far you raise your elevated tank so you can get more pressure, you can get more height, so that the water can flow very well. After that, the next thing you do is you look for a water source. Is it groundwater? Is it surface water? When you get a water source, please, you can be putting down these steps, even though it's in the PowerPoint. Then when you get the water source, you now ask yourself, what kind of treatment do I need? Or if it's groundwater, maybe I don't need treatment. If it's surface water, based on the water tests, what kind of treatment is possible? The most conventional, simplest, cheapest, most common treatment is filtration system. Filtration system where you have maybe sand filters, and then maybe you pass it through activated carbon, you pass it through UV light, pass it through chlorine dosing or other chemical dosing, depending on the result of the test. Is beyond the scope of this class, but it's good that you know it. As I always tell people in engineering, sometimes when you attend trainings like this, it's not because you don't know those stuffs, but it is to remind you of what you should know. Okay, so after then, the next thing you do is you now look at the layout and you do the water demand calculation. In doing the water demand calculation, we say you must take cognizance of 3 things. What is the population equivalent of the people? Maybe based on household, you might discretize it based on household. From household, you move to regions, from region, district, in terms of subsets, subgroups, clusters. You move into the clusters. Then when you do, you now calculate the total. That will be your average demand. However, in getting those demands, you might need to know if there are going to be future developments, where is hotels, where are industrial areas, where are commercial areas, where are residential areas. And if there are some unique features like factories that produces water, everything you must put into consideration, then you have to fall back on your material, which I've shared with us, and know what are the water demands. And if you can't lay your hands on those materials, please use Google, or fall back on any code and standard you can lay your hands on, and then know what are the design demand. For like hotel, for like hospital. Hospital is about 250 liters per capita per day, per patient per day. In hotels is about 200. You have it in your materials, okay? So you now know if it's hotel, 100-bed hotel, it means you do 100 by times 200. That becomes the water demand, okay? And I think that high value is because of things like swimming pool and other things. Then if it's a hospital, whatever it is, there are values that are standard for them. After then, what do? You now design your network. When you design your network, you now analyze your network and make sure that the network is working. And if you're analyzing the network, there are 4 things which we're going to talk about today. 4 key things you need to do. 2 of them are the elevation and the pressure and the demand. The other 2 is the pipe size and the pipe length. So that's what we're going to be talking about today. So before we do that, chapter 8 is one of the chapters that defines what do I call it? A design, the step-by-step approach for you to do your design. And for us to do that design, I'll quickly refer us to, let me get as a material, a case study. We'll be looking at one case study today. So that case study was what we'll leverage on. Yesterday, we did a case study about the general design methodology or fundamentals. Then today, we will now be looking at a typical case study. A typical case study. And let me quickly share that case study on our chat box. Somebody say I can't see them. Okay, just be patient. If you can't see them, either you just logged in or I'll post it. You get your materials. You're entitled to is your rights. So you're not gonna deny that. So this case study is a simple layout of a residential area. So here we go. So go to the chat box now and download that case study. Meanwhile, after the training, I think I will upload everything on our cloud. Remember? So can we see it? Branch system. There are two systems of pipe network design. We have the branch system and we have the loop system. So the loop system, as the word implies, is where you have looping. You loop one after the other. I'll show us anyway. Okay. So this is the case study. This is what we're going to be looking at today. We're going to be analyzing this network. It's just a simple network, okay? From what we said, if you recall last week, this map is enough, is adequate. Why? Because it's a map, number one, and it has topography. So this is what we need. And that's why in water design, the first person that goes to site is your surveyor. Your surveyor should go and take spot height. Know the level. In fact, if for any infrastructure work you want to do, whether sewage, sewer, stormwater, water, even road, it's always the surveyor that goes, because the surveyor will give you the X, Y, Z. It is the Z that we're interested in. And that is what you can see in this contour line. So the black dots you are seeing are houses, and these are the roads. Okay, so this is typical how a layout you request for or you'll be given as a consultant to do the water reticulation design. So your job is, when you see a layout like this, automatically, you don't need anybody to tell you that the overhead tank will be located at elevation 320. But somehow, elevation 320 might be the peak. So we now located it at elevation 310. And the lowest point in this network is 250. So if you do 310 minus 250, you'll be getting 60. So that 60 becomes the maximum pressure allowable in your network. And last week, I told you that the maximum allowable pressure must not be more than 8 bars. And here we have a geodetic height of 60 meters, which automatically, with the rule of thumb, translates to about 6 bars. So you can see this is cool. We are good to go. Okay, it means the maximum pressure anybody can get, not minding losses, is 6 bars. But you and I know that it cannot be more than up to 6 bars. It might be around 5 bars. If we look at 10% or 5 or 10%, we dedicate 5 or 10% for losses due to momentum change, losses due to pipe network, losses due to valve. The one for valve, fittings, bends, just incorporate it into the pipe losses, okay, or frictional losses. Remember, there are 3 losses. Losses due to height, they are PGH, due to potential. If you remember our Bernoulli equation, remember your Bernoulli equation, there are 3 losses. Okay, losses due to change in geodetic height. I'm in 2 meter height, you are in 1 meter height. The height difference between two of us is 1 meter. So automatically, 1 meter is my pressure ahead of you. 1 meter equivalent of pressure. Then you have the momentum flow. As water is flowing inside a pipe, there's a change in momentum, which is based on velocity, V squared over 2G. Remember our university days. Then the last one is the one based on H. HF, H underscore F, which is frictional losses due to pipe, because when the water is flowing in the pipe, there's a contact between the water and the pipe, so that leads to friction, so there will be losses. So the longer the pipe, the higher the losses. So this is our case study for today. This case study, when you finish, you are supposed to produce a map that looks like this. This is what your pipe network will look like. Okay, and this is your pipe network. So that loop system I'm talking about is when you consider these dots. When you consider these dots, you are looping it. And so in looping it, you use the Hardy cross method, which is a one kind of very complicated and taxing formula. But what I have seen people do a lot of time is the branch system. So if you are looking at this as a branch system, then you'll be seeing something like this. This is it. So this is a completely loop branch system. As the word implies, it's like a branch. This is storage tank. Okay, then this is the line going to one street, street 5, street 3, then continue with street 4, street 7, and so on and so forth. So this is what you expect to come up with if you are given something like this. Then the first thing you do is to prepare your calculation sheets. And your calculation sheet should look like this. Stay with me. Rotate pages. View. Yeah, please kindly rotate yours clockwise. Yeah. So this is what I expect you to come up with if you are using manual design, which of course I will encourage you. Computer application is just for model the system. It's just to model it and give it some form of simulation. So these are online training, so it can be difficult, but stay with me. Open the two files. If you have this, you can open it. So you can see, this is the point. Each of the points, storage tank to point 1, point 1 to point 2, point 1 to point 4, point 4 to point 3, and these are the corresponding lengths. So in any pipe network system, stay with me, there are 4 key parameters. You need 4 key parameters to design any pipe network system. Listen to me, gentlemen. Our key, what we're trying to do here in essence is to design the hydraulics, a pipe net system, okay? But just that before you design the pipe systems, there are protocols. There are things you need to do for you to be able to get the pipe system. So the two 4 parameters, 2 of them are node, I call them node parameters. And those 2 node parameters are simply, at every node, you need the elevation. What is elevation at every node, at every point? Then the second one, you need the water demand, okay, which we argued last week, whether we should call it water demand, flow, or what discharge, or whatever. And I said that they can use interchangeably, and it depends on the scale. Whenever you hear flow means something that is instantaneous, something that is dynamic, okay? It means it's per seconds, meter cube per seconds. When you scale it down to unit of 1,000, it becomes liters per second, meter cube per hour, meter cube per day. It's just a question of how you scale it, scaling up or scaling down. Then the other 2 parameters are what I call pipe parameters. So whenever you are doing any pipe design, ask yourself these 4 questions. Say, where is this? Where is the elevation? Where is the demand or the flow? Then for the pipe, you ask yourself, what is the diameter of the pipe? No, sorry. Pipe parameters. Then there, it becomes pipe diameters. Number 1, then pipe length. I think it makes sense. Why length? Because frictional losses is a function of length. Why diameter? Because diameter is the function of flow. Why elevation? Because elevation is a function of pressure. Why water demand? Because water demand is a function of the user. What the user wants is the quantity of water to come to his house, to come to a certain place. The elevation or the pressure is what pushes the water. Pipe diameter is what allows the water to flow. Pipe length is what helps you to measure how the flow is being impeded. Okay, and that will help you to design your pump. Okay, it will help you design elevation, and pipe length helps you to define the pump. Okay, it helps you to design the pump so that pump is not just to take care of the geodetic difference, the height difference, is also to take care of, to push it through the pipes. Of course, there will be resistance, there will be changes, and you have to push it in such a way that it will not lead to supercritical flow. Okay, it will push it within a certain velocity, which we discussed last week. Can somebody recall again the velocity range in every pipe network for water distribution? 0.3 meter per second to 3 meter per second. So that's the lower limit and the upper limit. The lower limit is 0.3. The water should not flow so slow. At the same time, the water should not flow so high in terms of the speed. So these are the 4 parameters. So I would like you to sink in, and I'll move over to my presentation once again. So here you can see the 4 parameters is what we're trying to achieve here.
Feature on your TCL TV, you can stream media directly from other devices.
Thank you. Please mute. If you want to say something, you raise your hand, or you chat me on the chat box. I'll get it. Somebody said I don't have the file. That's no problem. You get the files. You get the files. You get the files. Just take it from me. Okay. Now, let's move. So why do we need this table? Basically, this table is for you to tabulate those 4 key parameters. And the first parameter, as you all know, is the length. So this is the column for the length. So you are supposed to produce this in Excel. Yeah, you're supposed to get something like this in Excel. Take note of it. The next one is the demand. So this is the demand, liter per seconds. The demand. The next one, which is not important, is the slope, but you need it to determine the diameter. So you can see, first parameter you need, second parameter, support parameter, third parameter, and then finally, fourth parameter. The fourth parameter is the elevation at every point. The other parameter is the length of the pipe. So you can see that once your surveyor goes to site, or once you go to site, you automatically have 2 parameters by default. By default, you have 2 parameters. So your job as an engineer, as an infrastructure engineer, is now to look for the next 2 parameters. If you are able to get the other 2 parameters, your work is done. The other 2 parameters, which is not given, which is your work to do, then your work is done. All you need to do now is to begin to do what we did, what we're going to do now anyway. So you see, from the surveyor's data, I know the elevation, you took the spot height, here is 310, here is 270, here is this. All I need to do is to extract it in the form of Excel. Okay, form of Excel, and then I'll plot it out. Then these are the respective lengths of the pipe. So our job now is to find the demand. With the demand, we apply the demand and the slope, we get the pipe size. Then once we get the pipe size, that's finished. The other things you have here is check. Remember in engineering, when we do our design, we do check. You go back and check. Those of you that are civil engineers, when you do your design, there's this thing we call about quantity required, quantity provided. Sometimes when you do your design will give you Y16 at a spacing of 200. Well, you will say, no, I will use Y16 at a spacing of 150. You know, there's that, what is the meaning? There's one nominal design. There's a nominal design and there's optimized design. I think everybody does it. Those of you that are mechanical engineer, sometimes when you design the hydropower systems and it gives you a turbine with a head of, you design a system and it gives you a pump. Your pump of 15 meter head will take it. You, the engineer, will go and provide 20 meter. Not because you are wasteful, but It's part of optimized design, sort of. Okay, good. So now, so these are the things I want us to be aware. This is the layout. This is our distribution network, which you can do easily. Just follow the road network. Then finally, this is our calculation sheet, which we're going to do. So the next slide I'm going to show us is how do you come about to get your water demand. So to do that, I'll run through this slide and then we'll come back to it. So this is the working step. Step 1, work out the pipe layouts. Yeah, you'll see my screen. Work out the pipe layout. That's the first step. Okay. So then close loops. So for working out the pipe layout, when by seeing my layout, I know that I need to use a branch system here. By seeing this, I know that I need to use a branch system. Because if you look at it, you see that the houses are not clustered, they are branching off. So I've established that, so I'm going to use the branch system. So the next thing is determine the length of pipes and elevation of node that you get from your surveyor. Your surveyor will give you, when he's taking his spot height, he moves in 25 meters, isn't it? Or he moves in 10 meters, or he moves in 5, whatever, or 50 meters. So you can easily establish the length from one node to the another one, from one joint to another one. Okay, nodes are like joints. Okay, I keep mentioning node. So this is one node this is node 1, node 2, node 12. Node is the points where in conventional systems, you see the people putting, what do you call it? Water meter. Assume the node to be point of putting water meter, because if I put water meter here, it will take reading of all the people along this corridor. If I put the water meter here, it will give me the reading of all the people attached to this, and so on and so forth. Okay, so look at it from that way. In front of your house, if you are living in a well-organized estate, there should be a water meter. Just that everyone has their borehole. Okay, so it doesn't apply, but that's not what we're talking about here. We're looking at international best standard, how things are done from international perspective. So it's supposed to be, there should be a pump in the beginning of the estate, on the beginning of the street, so that if there is maintenance or if there is claim, somebody can go there and shut the pump. If water board comes, sorry, they don't need to go and give you estimated bill. They will just go there, open the manhole in front of your house, okay, and then check the reading of your meter, the last reading and the current reading, whatever, or use remote sensing, use GPS. That's by the way. So now, these are the first 2 steps. Work out the network, then work out the 2 pipe lengths. And when you work them out, that is why you have something on your table, 1 and 2. So this is the elevation, and then this is the pipe length. So that has been taken care of by your surveyor. The next thing, you determine the flow rates in each session. The flow rate in each session. And that is where people have problems. And that is where I want you to pay particular attention to, for you to know how to calculate the flow rate in each of these sessions. Now, that's number 3 thing you need to do to work out your network. Now, the flow rate here says maximum population divided by total inhabitants. Gross density over area with varying gross density. I will explain this in a very thin layman's language. He said divide total areas into areas connected to a certain node. Calculate or measure areas. Calculate flow rates to each areas corresponding to node. If you multiply these liters per seconds per hectare, this is water coming to a region. If I want to give water to a street, I can use what we call land use. If I use the land use will say, we are designing this place to be 200 people per hectare, 400 people per hectare, 600 people per hectare. Now get me. This is for a virgin land. There are two basic ways to design a district. Number 1, let's say no development. The first case, worst case, there are two cases. Let's say two cases. The two cases. So first case is where there's no development. No development. But in doing no development, there must be plan. The number two case is planned area already. Planned area, like an estate. Planned development. In the case of no development, the case of number one, no development, you make use of what we call land use. Abuja, when they design Abuja, let me give you an instance. Central area, they design it as what they call high density. Kuje, sorry if you're not in Abuja, you bear with me. In Kuje areas, for instance, they design it as low density, but now they've turned it to medium density, some areas medium density, some area low density. Places like Kado, going to Warempa, if you're coming from Banex to Warempa, sorry for those who are not in Abuja, I'm sorry, pardon me. Those places, if you go to the main control and say you want to build a house there, you cannot build anything less than 4-story building. Because in the section of Abuja, that 40 years ago, they designed those areas to be what they call high density. So when you say high density, you can't come and be building bungalow of 1 floor. No, you're building for 4 floors, 8 floors, 6 floors. Because they've already designed. So if you are designing that, if you are building pipeline in that area, you put a big pipe. Because for a 6-story building block of flats, in a 1,000 square meter, you might be getting 1,000 people. Whereas if you buy a 1,000 square meter in Jabi, in Kuje or Gwagwalada, it's only you and your family that will stay there. So you see yourself. Okay, another instance is your village. I don't know how your village is, but you find out that you can build your house in a large expanse of land. So if you are building a pipe network to that land, you cannot be using 3 inches pipe or 4 inches pipe. You just use 2 inches pipe, for instance, because it's only you and your neighbors. But take the same area, the same plot of land in Abuja, where you're going to buy it for 200 million, by the way, and you're going to build like 6 floors. 6 floors, 20 families. Each family is 10. So 20 families, 6 floors, 200 people. So you can see that in 1,000 square meter, you're already having 1,000 people, 200 people. Whereas in other areas, we're having 10 people with same size of land. So that's what we call using land use. The second option, the second scenario, is where there's already planned development. And that's exactly what we have here. It's already planned. The architects, the developer has already planned here. Duplexes, hospitals, schools, these. So it's easy for you to come and calculate the water demand. All you need to do is assign numbers. 100 liters per capita per day for residential areas, 60 liters for rural areas, for residential area, rural areas, 100 for residential areas, urban areas. Then hospitals, 200 liters per person. Marketplace, market people don't take their bath, so market will be like 30. They are standard for it. Schools is like 10 liters. We don't assign more than 10 liters for schools because it's just for you to go to the toilet, ease yourself, wash your hand, flush the toilet. Nobody takes their bath, nobody washes their clothes, nobody do the cooking, nobody even wash cars. In fact, sometimes they don't even have gardens to water. Their water demand is low. So you now know and discretize these things and take your time and state them, who has what, who needs what. Okay, so take note of those two scenarios. Is the place built? Is the place developed? Is the place not developed? With that, you'll be guided on what to use. Right? Good. So I think nobody has asked any question. So we continue. So this is the area. So we're going to do this. So the next thing you do is you now check for each of these nodes. How many houses are taking water from each of the nodes? Like this node 5 now. All the houses lying between 4 and 5, I will tie them to 5. All the houses lying between 9 and 10, they are taking their water from 10. So that is what this place is talking about. Each area, you ask yourself, how many riparian plots are converging, are within the watershed of, what's happening? Oh, sorry. F5. No. Okay, so the third thing is determine the flow rate initiation. Divide total areas. So what area are connecting water from a particular node? How many houses are connected to a particular node? You sum up the number of houses and then know that that is the flow in that area. The second one, these are the two methods for the undeveloped areas. You ask yourself, if I am doing 500 people per hectare. Okay, let me demonstrate it. The land use is with domain control anyway, or city development council. They'll give you land use. If you're building a house in Aja, Lekki, or anywhere you're building houses, the domain authority will tell you the land use. That's why in Abuja, when you do your design, sometimes when you do your design, take it to domain control, they'll ask you to go and provide for 6 families. Maybe you did for 1 family. They'll tell you, no, that place is not for 1 family, it's for 6 families. Then in some areas, if you do for 6 families, which is like a 2-floor or 3-floor, they'll tell you, no, that place is for medium density, which is for 2 families. What they are trying to do is just to regulate the population equivalent of that area. Now, watch this. Let's assume that we have 500 people, 500 hectares. I want to design for 5 hectares, sorry. 5 hectares is the size of land. And the domain control will now tell me that that place is, the land use for that place is 400 persons per hectare. Because the place is a bush, it's a virgin area. Then what this means simply means that the maximum number of persons we expect within that watershed, within that layout, is 5 times 400. So we are estimating that not more than 2,000 people will live there. PE. So if I'm now saying that 100 each person from what we did last week, each person is 100 liters per capita. Watch this, per day. If I now multiply this, remember this 2,000 now is also capita. If I don't want to call it P. Okay, it means I will now say 100 multiply by 2,000 and then apply my safety and I multiply by my safety factor. So let's assume the safety factor is 1, which it shouldn't be. It's 1.3 and 2.3. If it is 1, for instance, it means the quantity of water they need will be 200,000 liters. That's per day. Watch me, per day. C is gone. Also, somebody can also write this as 200 cubic meter per day. If I now scale it down, if I scale it down, then I'll say 200, and I want to convert to liter per second. 200 will be times 1,000 divided by 60, divided by 24 times 60 times 60. Which last week we said is just the same thing by as divided by 6,400. So if I do this now, let me do the calculation. 200, 1, 2, 3, divided by 6,400. It's giving me 2.3 liters per second. So this is now the water demand at the node where these houses are going to be connected. Assuming it's only 1 node, or the node, just the node before the tank, after the tank. So it means that I need water to be flowing at the rate of 2.3 liters every second for you to be able to deliver 200 meter cube per day, which is total water demand of that 5 hectares of land with the land use of 400 persons per hectare. Does it make sense? It does. So what I'll now do is I'll take this my 2.3, I'll go to my chart. and I'll get the pipe size, which is what we did last week. But knowing the slope, I have to also know the slope, and the slope is what I will get from my surveyor, because surveyor have taken a spot height at that point, and I've taken a spot height at the next pipe, the end of the pipe, So slope is vertical over the Pythagoras. You know what slope is? If I walk from here to here as a person, and this is me. So if I'm walking down here, and here is 0.310. Of course, here will be 0.290. And this distance is 200 meters. So my slope is this angle. Oh, sorry. And then by the time I walk this height, I have moved by a height of, say, 2 meters. Got it? So, what's my slope? No, I'm wrong. Sorry. If this is 310 and this is 290, that means I've walked 20. So let's say 2,000 meters. I walk 20 meters. It's quite a slopey place, because this is 310, this is 290. So the difference will be 20 meters, of course. So my slope, of course, the slope of the land will be and that slope will be here, the angle. Tan angle, whatever, will be opposite over hypotenuse, which is now 20 over what? 10 now. 20 over 20 divided 2,000. And that will give us what? 0.1 or 10%. Oh, whatever. The system is hanging now. Okay. Any question? Any question?
Not from me.
Yeah, maybe you can correct the 2,000 to 200 for the distance.
Do we grab it? I expect a question, or was it that easy? The second option says maximum population divided by the length. I don't normally use this number B. It said divide pipe network into sections. I've done that. Connected to a certain node. With the measure length of section. Calculate flow rate to a node. Determine the flow rate in section Q, beginning at end section. Good. Beginning at end section. Now, what this thing is saying is this.
Sorry, you're not sharing your screen.
For this case study now. If there's a node here, I'll calculate number of houses from here to here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, about 25 houses. So the houses connected to node 13, I'm sure that's node 13. The houses connected to node 13.
Sorry, you're not sharing the right screen.
Are 20 houses. So 20 houses are connected to node 13. So this becomes the demand at node 13. So what I need to do now is to establish the demand for one house. Okay, so this is node 13. So there are houses connected to node 13. This is the most difficult place for a lot of engineers, and this is where this training, why we are doing this training. This is where people have problems. There are houses connected to this node 13, about 25 of them. So all you need to do is to determine the demand for one house. You multiply by 25. That becomes the demand at this node. So if water board come tomorrow or somebody come to take measurement, all you need to do is to know the consumption of everybody along this line. You will just come and open this place and take reading. Okay, I'm sharing it now. So here I'll count the number of houses here and then calculate their total. So what we need to do now is to establish what is the, I'm cleaning this now. What is the demand for one house? So what kind of house? So let's say we are designing for a let's say that each of those black dots houses is a 4-bedroom duplex. 4-bedroom duplex. So 4-bedroom duplex, let me ask you, how many people do you expect to be in this duplex? Let's say we're expecting 15 persons. Oh, you say it's too high. Yes, it's okay. I say it's better to over-design. 15 persons. Okay. Now, what is the water demand? Water demand requirement based on US standard, WHO standard or one standard. WHO say 150. You and I know that 150 is not achievable. Although if you use 150, you can use a lower safety factor to come to something. But let's use 100 liters per capita per day. And let's use a safety factor. 2 means 200%. That means we can never make mistake. That means nobody can ever complain about water. It's absolutely not possible. Okay. While this training is going on, let me respond to some messages we have. So here you have 4-bedroom duplex, 15 persons. Water demand per person. I'm supposed to have put per person. Water demand per person is 100 liters per capita per day. A safety factor is 2.2. Therefore, their water demand will be 3,000 liters per day, which is equivalent to 3 meter cube. It's just the same thing. Convert it to seconds, you have this. Therefore, we are looking for the water demand calculation. So that's water demand calculation is what we're doing now. So this is water demand. So here is where we are. So I'll copy it out. And so water demand calculation. So we start with the lowest node. Look at it. Say start with beginning with the lowest node. It's a divide pipe network into sections connected to a certain node. Measure length of sections. Forget about this one. Just calculate the flow rate. So we want to calculate the flow rate to the node. Calculate flow rate to the node. We're using this first one, A. So the flow rate. So let's start with node 13. How many houses are connected to node 13? This is node 6 here. This is node 6. Between node 6 and node 13, there are about 25 houses. and the demand for one house is 0.035. Therefore, for node 13, we can comfortably say node 13 will be 25 houses multiplied by the value of one house. So this gives you the flow per seconds that will take care of those 13 houses. So that is 25 times 0.035. It's giving me 0.87. So 25 houses need a flow of 0.87 flowing through the node every second to satisfy their water demand of 3,000 liters per day. So this is the one for node 13. Next, we move to the upstream of node 13, which is node 6. So you go back to the drawing, you ask yourself, what is the area connected to node 6, or what is the number of houses, since it's already a planned development. So if you come here, you see we have 1, 2, 3, 4 houses. And we say in water demand calculation, you need to project for the future. So let us assume that the opposite road, opposite plots will also be built in the future. Therefore, number of houses connected to node 6 will now be 8. I can count 1, 2, 3, 4. But if I mirror it, if I assume that next year the landlord of these lands will get money and pay and build their own house, I'll project that. That is part of what engineering is. So when I project that, it means I'm designing for 8 people. So for node 6, I didn't share that. So for node 6 now, we have 8 people. 4 this side, 4 the other side. The other side are not unbuilt, but they will be built. Is in the plan, is in the layout. So now I'll do 8 multiplied by the demand of one person. So that would be, so for node 6 now. So move to node 6. So node 6 will be what? 8 houses multiplied by what? 0.035. .28. So can you see? Node 6 is 0.28. So that's the water demand in node 6. Now, this is the thing. This is the big deal now. The big deal is this. The water demand, the water demand for node 6 is 0.28 or for 8 houses. But the base demand is the value of we got here plus the value of the downstream. So the value I got here plus the value downstream. So instead of writing node 6 to be 0.28, I will say, so node 6 is not 0, we got 0.28 for houses between 7 to 6. But then node 6 already has a offshoot or has somebody downstream that for water to get to that person, water must flow through him. So it means that node 6 is accommodating its own demand and the demand of the person going downstream. Therefore, node 6 will now be 0.28 plus 0.87. That will be the value for node 6. It's complicated, it's difficult, but that is why many people get it wrong. And that's why this training is important. So this is the value for node 6. Therefore, let me use that word. Node 6 through node 6 now will now be equal to 0.28 plus 0, no, plus node 13, which is equal to 0.28 plus Are you with me? That will be 1.15. So that becomes the new demand. That becomes the new demand on node 6. So I'll go to my table. I'll fill it in. So if I come here, this is the node, this is node 6 to 13. So this is 6. So here I'll fill in 1.1715, sorry. Then under node 13, where's node 13? This is node 13 here. Here, node 13 will be 0.87. Node 6 will be 1.15. So here will be 1.15, here will be 0.87. So 0.28 is just the demand of node 6, but the real demand, the base demand is different. The base demand is different. Any question? Any question? Any question? No question.
Yeah, okay. We need that sheet.
Yeah.
You didn't share it.
I did. I'll share it again. Is in page 3. If you're looking at page 1, you will see only this man layout. Or you don't have it?
We're always seeing the demand calculation.
Okay. Okay. You mean I didn't share my screen? Yeah. Okay. Sorry. So here, this is node 6, 1.15. You can write it down. Okay. What we could do is maybe, I don't know, our assignment, we will have our assignment between now and next week. I have something like this, but if I start looking for it in my system, I'll waste some time. I know I have one I have filled. That will make sense. It's better you know it. Okay, let's continue. Let's get the process first. Let's get the process. I'll look for something I've done in the past. So the next one is node what? Which node is the best? Before you do node 7, you must have done node 11, because node 7 will be node 6 plus node 11. Yeah. Let me demonstrate it with this. Let me demonstrate something. If this is a main group, it now gave birth so this is the tank, water tank. As water is coming in, let's say the tank has 500 liters or 50 liters of water. When it comes here, if 10 liters flows here and 5 liters flows here, or 20, sorry, or 15 liters flows here, automatically all will be flowing here will be 25. And if here is 25, it means that if I ever say that here is 5, here will automatically be 20. Then let me continue. If this place is 20, and here is 10, automatically means I must create a link That'll be 10. No need for a symbol. Unit, sorry. So can you see it? So water comes here, 50 liters. It gets to this junction, it's still 50 liters. 10 liter flows here, 15 liter flows here. Definitely 25 liter will flow this way. As it gets here, 5 liter diverts, 20 liter will continue. So the question now is, before you get these 20 liters, you must get 10 and get 10. You get 20. Before you get 25, you must have gotten 5 and 20. So that's exactly how to do this pipe network. So this thing can be long, elongated as it's coming, is branching off, and that's why you see pipe sizes are increasing or they are increasing based on the population equivalent. So here, let's continue. We'll do node 11. How many houses are connected between 7 and 11? How many houses? How many houses? Just count. If you don't count, I'll give you 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 houses. 10 houses. How did I get 10? Look at it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's where the thing is spotted. So 10. So I will go to whiteboard. I need to clear some things. Ten houses. Instead of doing 10 times 100 times factor of safety, I've already done for 1. So there's no need for that again. So that will be 0.035. That will be 0.035. And that will give you what? 0.35 liters per second. Therefore, once I get this, then I can get node 7, right? I've gotten node 11 as this. Therefore, node 7 will now be this, plus if your house is connected to him. That one usually confuses people. And sometimes I just feel like keeping it silent. This node now, node 7 will be node 11 plus node 6 plus its own demand. Plus its own demand. Stay with me. Node 7, try to know where node 7 is equal to node 6. You don't need to mention node 13 again because node 13 is inside node 6 plus node 11 plus itself. So what is node 6? Are there houses connected to him? That's the next question. Okay. Look at the drawing. Let's see. Yeah, there are houses. There are 1, 2, 3, 4. So if you are doing times 2, it will become 8. So here, node 6, node 7, his own demand is already 8 houses times 0.035. hold on, 0.035 times 8, 0.28. Therefore, node 7 will now be equal to node 6. And what is node 6? 1.15 plus node 11, 0.28. Plus 0.028 for itself. And what's total? Sorry, 0.28. $1.71. Next, we want to do node 8. You cannot do node 8 until you have done node 7 and node 9. We have done node 13, node 6, node 11, node 7. But node 8 is node 7 plus node 9. That's the value of node 8. So we don't have the value for node 9. And unfortunately, again, node 9 is node 10 plus node 12. So the next node we're going to do now is to do node 12 and node 10. We add it up, that'll give us node 9. We add node 9 to node 7 to give us node 8. Please, any question? Is it confusing?
Sorry, I just want you to affirm the calculation for node 11 while you are calculating node 7. You put almost the same figure, 0.28.
Oh.
And I think it's supposed to be 0.37, 0.35 rather.
0.35, yeah, thank you. Right? So let's move to node 10 and 9. Node 12, sorry. So what is node 12? Node 12 is, let's now, gentlemen, we'll make assumptions to move. I'm going to count these two houses into node 9. I'll count these two houses into node 10. It's the same thing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 houses. Then this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 houses.
Sorry, you're not sharing your screen.
Uh-oh. So we're going to do node 12 and node 10. How many houses are along node 12? How many are along node 10? So if you look at it here, you see. Now let's play smart. These two houses here, to make it easy and simple, I'll count these two houses into node as part of node 12. I'll count these two houses as part of node 12. Someone can query it, but it's okay. I'm doing it for simplicity. I'm doing for simplicity and ease of calculation. So these two houses here, join this one, these two. The most important thing that at the end of the day, they'll add up. That's the beautiful thing. So what do I do now? What do I do now? So I'll go back to my whiteboard and say node 12. Node 12 is straight hand, 10 times 0.035, which will give me 0.35. Node 12, node 10, same thing, right? Right? Therefore, node 9 is equal to node 10 plus node 12. No need to say its own node, because its own node have somehow shared it along the downstream nodes. Take note of that. Therefore, node 9 is now, what is node 10? 0.35 plus 0.35. That should be 0.7. So I've gotten the value for node 9. So now that I've gotten the value for node 9, node 8 simply becomes, because if you look at it, there's no houses between node 8 and node. The base demand for node 8 is 0. So it will now be node 9 plus node 7. Remember, I'm not considering these dotted lines because I'm using branch system. So I'm not considering the dotted line because I'm using branch system. Take note of that. So now, node 8 is now node 7 plus node 9. What is node 9? 0.7. And what is node 7? 1.78. So one thing you must see is that as you are approaching upstream, as you're going upstream, the pipe size is increasing, the demand is increasing, but as you're going downstream, the demand is reducing. That's why you don't use one type of pipe. As your pipe is coming in from the storage tank, it's reducing. Just to check in your house. From storage tank, you use 2 inches pipe or 1.5 inches pipe, 1.5 inches pipe. As it's going to inside the house, you start using 1/2 inches, 3/4, and what have you. That gives us 2.48. Right? So next, we are going to do node 4. But before you do node 4, you must have done node 5, node 3. We have node 8. So let's quickly go and do node 5 and node 3. So let's start with node 5. Node 5 has, in real sense, in practical sense, so some of these things that look like bigger than others could be schools, hospital, hotel, industrial complex. So those ones, you treat the water demand not as a flat rate, not as flat as we've been doing. You know, we assume everyone to be the same sizes, to be the same prototype, be the same type of house, be the same number of occupants or standard of living of occupants or whatever. But in real life, that house looks more like a hotel. So I'll go and calculate it separately and add it up. So, but let's assume all of them are residential. But this one, I'll assume it to be 3 houses in one. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, about, let's use 15 houses. So 15 houses for node 5. So node 5. 15 houses. $15 times 0.035, 0.52. as the demand for node 5. So let's take a look at node 3. Node 3 somewhere here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's count this one as 3. 17, 18. Okay, 18. Let's just do 20 houses so that we don't do too much calculation. So node 3 has 20 houses. It might not be up to that, but let's assumption, okay? Now, so that will be 20 times 0.035. I think that will just be times 2. 1.04. Therefore, node 4 will now be node 3 plus node 3 plus node 5 plus node 8. Please, any confusion here? Are we all following? The quiet is so quiet, so cool. It could mean two things. Either you are understanding everything I'm saying, or you understand virtually nothing.
Yeah.
So which of the two?
Following.
Hello? Which one is your reality? You are getting everything, you understanding what we're doing, or you are lost?
No,
I hope it's the first one. Okay,
I'm definitely following.
Yeah, I'm
okay,
following.
I'm following.
Okay, thank you. It's all right. Okay, so I'm happy to hear that you are following. Therefore, node. Okay, Michael, raise his hand. What's the question?
Yes, it's just a clarification so that you can further enlighten us. Now, if we look at the drawings again, particularly from one node to the other, assuming that where we are treating right now, that is a node 4, and then trying to determine what node 4 will be, considering node 3, 5, and 8. Now, we can also assume that from one node to the other is like a street.
Yes.
And then you can see that on a particular street, we have buildings to both left and right of such street, while in some, we don't have probably on the other side. For instance, from node 1 to 4, the houses are on one side.
Okay.
But the ways and manner we are doing the calculation is almost similar. So what can we really say? The consideration we have to give when things like these surfaces, like where we don't have buildings on one side, do we still have to project and assume that buildings are there in our calculation?
You have to project, sir.
Okay.
If you are on the first day, we say that you project your population for 25, 30, 40 years, depending on what your client wants. In fact, you can project for 50 years. I say in Nigerian case, if you are doing a water recirculation system, project for 50 years. So those empty plots, there's no way you will tell me in 50 years' time or in 20 years' time, properties will not come there. And that's why properties that will come there should be what is designed, as in what is in land use. Because there's a kind of, if you go and put industry there, something like that, you might end up denying residential people water. So in summary, yes, you will assume that somehow what houses will come there. And that is part of why the population will increase. That's part of what makes the population to increase.
That is okay. In which case that at this present time, we should be probably expecting that they will receive more water than expected. I mean, the demand will be higher than will have been.
Yeah,
I mean,
no,
their requirement now.
Yeah, you see, if we are supposed to supply 10 people water and you supply them water for 20 people, what it simply means that they will consume the water in 2 days. Did you understand?
That is right.
Yeah, so if you supply them excess water, well, it simply means your pumping time it reduces. I mean, they can keep it in their tank until they need it. They can have 1 day reserve.
Noted. That is noted. Thank
you. So thank you, sir. So number 4 now is the demand of number 3, demand of number 8, and demand of number 5. So let's do that one now. We're on time. So note 4. Note 4 is now note 4 is now note 3 is what? What is the value of note 3? 0. Can somebody help? Note 3 0.1 point, sorry. 1.0 plus what again?
0.52.
Note 5 plus note 8.
2.48.
2.48.
So we add up 1.04 plus 0.52 plus 2.48, 4.04.
Excuse me. What of the houses along the 1 to 4?
Sorry?
The houses between 1 and 4.
Are there houses there? Forgive me, are there houses there? Let me check.
1 and 4.
Oh,
whoa.
So we need to add 8. 4 divided times 2, that's 8. And 8 is 0.28. So this will be plus note 8, then plus base demand. Thank you, that's a good observation. So it means here will now be plus 0.28. So here will be 3.2 now. Then note 2. Note 2 should be anything 0.28, right? Don't need to start doing the calculation. It's not even up to that. Let's assume, let's give him 7 houses. 1, 2, 3, 4, 8 houses. 8 houses. Let's assume there's another development coming here and the one development is coming at the end. Let's assume this is node 2. So let's assume that this empty plot is 1 house. Then let's assume that there's another empty plot along the end. Assumption, approximation, please. So this is now 8 houses. So that will be 0.28. Therefore, node 1 will now be node 2 plus node 4. Node 1 will now be node 2 plus node 4. Node 1 is now what? Node 2 plus node 4, which is 0.28 plus 4.32. That will be
4.6.
4.6 liters per seconds. Now, if you convert this thing, if you scale this thing up, convert it into, this is the hourly peak flow. This is the hourly peak flow of water that will certify the entire layout. So we have discretized it. What we've done, many people don't do it. What they do is they just calculate the number of houses and they get you 4.6, but which is good. It depends on your scale of your design. This thing we're doing now is because of the purpose of learning. I don't need to do it. What I need to do is to measure the entire area and multiply by the land use of the plot expected. I will get 2,000 or 1,000 people. And I'll multiply by the population equivalent. And this 4 points, remember we did it this morning for 2,000 houses or so thereabout, and we got 2.3 at a go. We didn't come to break down all these things, but breaking down these things is just for you to understand how it is done. Okay? So if you now get this 4.6 now, this can use it to design a nominal tank. I repeat, you use it to design a nominal tank, but I will still show you how to design a normal tank. When you're designing tank, a tank is made up of 3 parameters. What we call emergency volume, 1, firefighting volume, and then base volume. So the base volume is a percentage of your total volume, because then you add volume, three things is in your manual, is in your material I'll share with you. You now add emergency volume. Maybe there's a repair. Maybe there's a pump breakdown. Pump breaks down, there should be water for people to use for, let's say, 6 hours, 8 hours, 1 day, 2 days, depending on your design criteria. Then you now have firefighting volume. If you're designing for firefighting, there should be some quantity of water in your tank that at every point in time, there should be water to fight fire. So that's how to design tank. But nominally, in Indian design, when we have standard design, we have nominal design. Nominal design, if you want to choose, you can call it the lazy man's design or the rule of thumb design. But it works. It works if you apply appropriate safety measures. Okay. Last week, I trained people from water resources, and I told them something that we do in doing reinforcement. If you want to calculate the number of reinforcement, I told them, I said, the only thing you need to do is to calculate the concrete volume you need. You don't need to start doing bar-bending schedule or asking for structural drawing to do bar-bending schedule. You're wasting time, because even the BS standards have told you that for every 10 cubic meter of concrete, sorry, those who are not civil inclined, you need between 75 to 100 kg of reinforcement for non-structural members. Then for structural members, you need about 100 to 150. Then you, the engineer, can now start to optimize, depending on whether you are building a car park, a jetty, depending on the structural significance of what you are building. So for me, once I calculate my concrete volume, I can determine the reinforcement I need. So all I need to do now, I'll now go and use the unit weights of maybe Y8, Y12, Y16, and then get the number of length or get the appropriate tonnage. But this is tonnage I need. Okay, that is not for this class. So now, to do a nominal design, if you convert 4.6 liters into seconds, convert it into meter cube, because that's a more standard for tank design per day. Pipe, this one is for pipe. I love this. And this one is for tank, because tank talks about daily. Is a more upscaled temperance of scaling. Okay. Then the pipe is also a temporary downscaling. So it's like you're downscaling into you're discretizing it into the minimum units. Whereas for the tank is usually few per day or half day. For pipe, we expect you to have water in your pipe at every second of the day. Somebody say, how do you calculate water demand for firefighting? You calculate it by standard, sir. The standard I can remember is that you calculate it by those things we do in civil engineering. 1 hour firefighting, 2 hours firefighting. So you will decide, is it for 1 hour firefighting? Some of us don't do that. When we say firefighting, what we are just saying is that water that will hold the fire until fire service arrives. Sometimes it's not really the water that will quench the fire. If it quenches the fire, lucky you. But it's the water that can be able to arrest the fire until the big man comes. So for 1 hour, this water is enough for us to fight this fire. For 2 hours, this is the water to fight fire. From German standard, this is standard. I know that it's about 48 cubic meter for a 2 hours 1 hour firefighting. But I need to go back and browse my internet to get to the standard. So it's a standard thing, okay? It's a standard thing. And it depends on scale also. So it depends. I think this is for 2 hours, sorry, not 1 hour. So it means for 2 hours you can battle the fire. Just like we talk about cover to reinforcement and all those stuffs. So it's a table, it's a chart. Just pick it up. So let's convert this guy. So if you convert this guy into meter cube per day, what we need to do is to multiply by A6400 and divide by 1000. So it's giving us 398. So I need a tank size. Give me this. Watch me now. I need a tank size of 398 cubic meter per day. That's what will service the people per day. So if I want to provide a daily pumping, 24 hours pumping for the water demand, this is the size of tank I need. So let me put it into perspective. Tank is length times breadth times height. Now let's fix one. Let's fix the height at 3 meters. If I fix the height at 3 meters, I'm not done yet. Let me also assume that the length will be 2 times the breadth. So more like perfect rectangle, sort of, maybe breadth tank. Therefore, the volume will now be length times 2b times 3. And I'm expecting it to be around, to give me 398. If I multiply, length is 2b, yeah? So this will be, yes. So this becomes length, right? Of course. So that will give me 6b squared. I don't know how to do square here, please bear with me. Three, 998. So B square, let me put it this way, will now be what? 398 divided 6. 66. So 66 is almost 64, which is square. So that will be B is equal to 8. Therefore, the tank is 16 meters. It won't work now. By 8 meters, by 3 meters. So for a community like this, you cannot provide 1 day storage for them. So what you do, you provide half-day storage. And when you say half-day storage, it means at this point, just stop me. Uh-oh. So it means for 12 hours pumping, I need to do 12 hours pumping. That means I'll pump twice per day. So for 12 hours pumping now, it means the tank size we have. So here that I put 398, with 398 divided by 2, because every 12 hours, I'll fill the tank. 398 divided 2. So I actually need a tank size of 199, which is almost like 200 cubic meter. So now, if I go back to my formula again, it will still be the same thing, which is 6b squared equal to 199. 199 divides 6. So that will give me 33. So b squared is equal to 33. So if I do 33, I think 6. So that will be 6, b equal to 6 meter. Therefore, L is equal to 12. 12 meters size tank. You just to do 2 tanks. I mean, you understand? So it will be 1 tank, okay? Because let's say grand tank, for me to do a 12 meter tank by 6 meter by 3 meter, or I will increase these 3 meters to 5 meters, right? So you can play around with it, but I just want you to understand the concept. But this is for 12 hours pumping. So if I change this height to 5 meters, so it means here I'll be dealing with 10. If I'm dealing with 10, here will now be 20. So you'll be having around 4 meters. So you will be around 4 meters by 8 meters by 5 meters. So I'll be getting like 4 meters, 8 meters by 4 meters by 5 meters. So it depends. It all depends. So now we have done the last calculation. Well, I think we've gotten notes, all the notes, right? Now, my assignment for you is this, just to make it sink in. If you go home, please fill this. That will be the first thing I would like you to present to me. And if you build this in Excel, you will have it for life. Or can I even say you can go online and you can get a lot of templates. You can go to online and you say templates. It will bring you one for sewage or something, but you can edit it. Templates for water reticulation. Now watch this. Watch me. You put the white card. This white card, star S L S. Star LSX means
that we are not seeing what you're doing, sir.
Okay, I just want I want to get some of these templates. Because I say our assignment for this week is for us to go and produce these templates in Excel. And then all this value we fill them here. Look at the liter per seconds. Then the next thing is to size the pipes. So by next week, I will size the pipe, but I'll show you how to size the pipe now before I go. I think I did it last week even. I also gave us assignment last week. Okay, so develop this thing. So I was trying to emphasize what I emphasized last week, that when you're doing design, Google is your best friend. If I go to Google and I type templates for water reticulation design, star XLX, star LX means Google, give me only those files that are in Excel. Because when I say templates for water reticulation, it will give me millions in PDF, in any kind of file format. But I want it to be in Excel. So I'll type enter. And what it's going to give you will blow your mind. It's going to be electrical Excel spreadsheet. You think it's a joke. So water system design templates. This is templates. They are just there. National ranking water is just there. Just search, search, and search. All plumbing design templates. I don't know which one to do again. So I'll definitely, by the time I go through it, I'll get wonderful templates. Okay, you see? So these are templates. Of course, some of them, you need to pay money. See, it's asking for membership, it's asking for money on Indian guy, or whatever, but that's just by the way. So, I mean, to build this in Excel shouldn't be rocket science. Come on. I have one, but I can't, if I start looking for it, I will take our time. Okay, so the next thing you do, okay, Negedu, you raise your hand, ask your question.
Can you just send us this template so we can recreate it ourselves?
I've sent it, it's yours, it's there, it's part of your material, okay. But I'll send it again. I'll send it on the platform too, WhatsApp plan. So after number 3, what's the next thing you do? I've done everything you're supposed to do, but let me also take you through them again. You now work out for what we call determination of service pressure, minimum service pressure. Service pressure is what pressure do you want to attain in your network? Let's say I want a pressure of 2 bars. How do I get 2 bars? You ask yourself, in that layout, what is the highest number of floor? Because your reference point is the person is the highest floor in the estate. Now, take note of this. If you are doing your design, if it's a place you have 2 floors, then your reference point will be 6 meters. So it means that 6 meters becomes your minimum service pressure. It means anything you are adding height, you're already adding 6 meters. If you are building an elevator tank, you're already adding 6 meters to anything you want to build, because the highest building is already on 6 meters. But as you know, we do it in terms of meters. So service pressure, in German standard, the service pressure is 22 bars or 20 cubic meters of water. So if you're adding a service pressure, you must consider 20 meters because of high-rise buildings. But it depends. Some places your service pressure might just be 10 meters because it's a bungalow house. There are bungalows, and bungalow is like 5 meters maximum, right? Or even 3-4 meters. Or let's say 1 floor, 8 meters. And you already, so you just add some small factor of safety and say, okay, my service pressure is 10 meters. It means that anything you are doing, you're playing around with 10 meters. If you are providing overhead tank, it cannot be lower than 10 meters. So 10 meters is off it. So that's the 4th thing you do. The 5th thing you do is you determine choice of your K value. Here, the choice of your K value is simply a function of the type of pipe you are using. Last week, I shared with us the nomogram. That is for a pipe size of a PVC pipe, ductile iron, and concrete pipe. It's important that if you're doing your design, water design, you from ahead of time, you determine what kind of pipe I'm going to use, because it will help you to calculate the losses. It will help you to calculate the losses, right? Then the next one, which is number 6, you now determine the elevation of your storage tank. Some people will always ask you, at what height should your tank stand be? Well, it's very simple. your tank size should be the head difference between your tank size minus the service pressure divided by the total length of slope will be your I. You first of all get your I, your admissible slope. Then another way to get your admissible slope, watch me now, is that lowest water level minus the surface pressure minus geodetic head divided by the length. Remember, I showed us Pythagoras. So this is just like Pythagoras. But you do summation of length from point 1 to point 2, point 2 to point 3. What's the total length? Then divide it by total height. And that total height is the level of water. And choosing the level of water, you choose the lowest water level. If water is above that, to your own advantage, meaning more height, more pressure, more quality. Okay? Remember, even your tank, you should observe freeboard. So 70% of the tank or 60% of the tank is enough to use it as minimum, or 20% of the tank. Then minus service pressure. Then minus the height of the building. That will now give you the total losses. Then with I, you now dimension your Q as a function of discharge, slope, and K. K can be 0.1, 0.5 based on the pipe material. Then you now take use of, what do you call it again? You now make use of your I. By I is Pythagoras. Change in vertical height minus change in horizontal height. That is this grammar here, or this you are seeing here. Summation here means pipe section plus pipe section plus pipe section until you get to the end of the pipe. Then this place is the highest water level in your tank minus the service pressure. So I don't know how to explain this thing now, but let me quickly do it. I'm ending this class in the next 10 minutes because we had 10 minutes grace. This is somebody's house. This house. This is somebody's house. This is somebody's house, okay? This is somebody's house. If this is somebody's house, for instance, and forgive me, let me just demonstrate this. This is a thatch roof. This is ground floor. This is first floor. And here is the tap level, maybe shower level of shower, or here. And here is 3 meters. Here is another 3 meters. And my tank is somewhere here. This is the limitation of online training, but it's okay. You can't help it. This is my tank. So if I take the height difference between the highest level of water in my tank to this place. So the difference, so this is the height difference. This is the highest level. This is now what we call change in H. Delta H. I can't type it here, sorry. This is delta H. Here is the geodetic height difference. So the point I'm making now is that you don't go and say the water level, the highest level, the service pressure is on this person. You use the person on the higher side. So that is why here, like now, you ask me now, this is our 6 meter. This is 6 meters already. Now, if this is 6 meters, and I want the service, this is 6 meters. That's the height difference. Then I want a service pressure of 10 meters, which is 1 bar, right? It means that this tank now will be 16 meters. That is just the point. Case closed. That's the grammar I'm trying to speak. Yes. This is the difference. Though if you check it very well, this person will get water at 13 meters, which is 1.3. Why this person will get water at 1 meter? Pressure. It's okay. But don't use this person on the ground floor as your reference. And that's exactly what this place is trying to refer to. This is it. This is how you get it, your slope. Then once you get your dimensioning, you now use the nomogram. You use the nomogram to determine your from your table, which I showed us last week. I've shared with us. Once you get your Q, you use your nomogram to determine the diameter. Okay. So number 8 is you get your Q. Then all these other ones are not necessary. This one, the service pressure is 30. And the maximum service pressure is 80. So 8 bars or 3 bars. So pressure will be between this and this. So, but if your tank is not fixed, if the elevator tank is not have not been fixed, in other words, you didn't have a presumption of what you want your service pressure to be, then you just dimension your Q as a function of discharge only. So this one is more talking about nominal design. Okay, so you say you now go back to step 8 to 13, like before, but beginning at the end of the system. So this is what we just did now. Later you can read this. If you don't understand anything, you can call on me and I will put you well. So after this now, like we got 4.6. So let me design the primary pipe only. Let me design the primary pipe. So I'm using PVC pipe. So I'm going to use a monogram of 0.1. I'm not going to design the primary, the secondary and the tertiary. No, as I said last week, once you design the, so I'm going to design the main pipe. And that main pipe is the one coming from the water tank. And here we got we got 4.6. So this is 4.6. So let me say 5. I don't know the slope, but let me assume that the slope is 0.5 or 5%. Yeah? We can do it. We can do it even in the drawing. You can do it because we are giving it one contour. But for want of time, getting a slope an engineer should be a big deal. So 5 against 5%. So what I'll do is this is 5. I'll read 5. I'll go up. I'll go up. This is 5%. 5% is falling between two pipe sizes. I'll choose the bigger of them. So under 5, which is 4.61 anyway, I'll go up. This is 5 here. Oh, sorry. Five. I'll go down. 5. 0.5 slope. If you convert the percentage, is this. Then you see it's giving me 100 mm. 100 mm pipe. The other first pipe is about 80. So it is anything between 80 and 100 will do it. But the law says you take the biggest one. So the bigger one or the closest one to this one is this pipe. And this one is what? 100 mm diameter pipe. The discharge is here. If you go down here, you get the slope. And that velocity, sorry, the velocity is 0.6 here. Look at it. 0.6. So the velocity at that point is 0.6, while the pipe size is 100. So those are the two parameters you need. What is the velocity? Because you don't want the velocity to be lower than certain value, and you don't want the the pipe size to be inadequate. So that's how to define the pipe size. So next week, we're going to do more and design more. So I'll